All right, welcome everybody to today's TVM Open Development meeting. We do not have a large audience today, but we do have a topic on the agenda, so we will have a conversation for the record. We may quite likely revisit this topic if we do have more attendance in the next session or later than that. But it's an interesting idea, one that would be a sizable change to relax, so certainly worth discussing. This is an idea that's come up in a couple of Eric Lunderberg's PRs regarding having an unknown purity value. Rather than using true false, we could have pure, impure, and unknown. So I'd like to invite Eric to introduce the subject.
Thank you. Yeah, this initially came up when, say, trying to have slim to relax translations, say, follow the appropriate relax, say, conventions for having well-formed outputs with correct purity annotations. And turns out that there ended up needing to be wider changes on the relax side to avoid introducing overhead for say edge cases for recursive functions. So the initial goal is if you have a slim operation like print, this is something that right now is not handled correctly when being translated to relax. All slim to relax conversions produce outputs inside a data flow block. And print, being almost your prototypical impure function, is not allowed inside of a data flow block. And so this is something where, at the moment, this can produce inconsistent optimizations because you could have or depending on what passes assume that their inputs are well formed, what purity checks they do later on, what things they remove or reorder. And so this is something that we should resolve. In doing so, it then becomes a little bit tricky because, see, ideally it would just be we put nothing into a data flow block, and then we apply the handy-dandy, say, convert to data flow pass as a post-processing step, and now everything for which it is legal to have a, say, data flow block around is contained within a data flow block. However, this ended up running into issues because we now have functional purity for subroutine calls, and those subroutine calls might not be known yet at the time when they are being used. And so there were two folds to this, or two approaches to this with somewhat overlapping PRs, one of which was, let's just infer the functional purity from the body if it's not specified. The relax purity is still either true or false, but instead of defaulting to always pure, which is what the default values both in Python and C++ currently do, we'll instead default to inspect the local function body to determine the purity. This isn't a perfect step because because you can have self-recursive or mutually recursive functions for which, say, local inspection is insufficient. You can have forward declarations in TVM scripts where we would like to have the purity be inferred, including all of these subroutines. And this starts being the same problem that we have with, say, struct inference for subroutines, in that we don't have enough information until a final post-processing pass. For struct inference, we can avoid introducing incorrect information by falling back to object struct info to say, well, we have a subroutine that doesn't tell us what it returns. We could default to it returns arbitrary unknown thing and then just fill in the blanks later on. However, we can't do that with the current purity annotations, because the default of pure is something that the user could also specify. It's something that is what we'd like to infer. And so really the problem is that we're assuming the special case rather than either letting the user tell us that it's the special case or proving for ourselves by inspection that it meets the special case. And so the other approach, and this is sort of going from the relax IR outward, is let's introduce unknown purity, where same way as we have unknown object struct info, we have, or we could have unknown purity. Now, from a theoretical perspective, this is absolutely equivalent to just it is impure, because every pure function is an impure function. It's a subset of it. Any context where you can call something impure, you can call something pure as well. And so the optional is a bookkeeping utility for our use, because there are two types of impure that we would like to distinguish between. There's, we have inspected it, we know that it's impure because we found an impure call somewhere inside it, and we don't need to inspect it again. And on the other hand, there's, we don't know if this is impure. It might be calling a function with uncertain purity. It might be that it calls itself. It might be that the user just didn't provide an annotation and local analysis alone will be sufficient. But we need to have a way to specify, I don't know the purity, as distinct from this is impure. If we want there to be or if we want to avoid performance issues during compilation, where what is possible with the current relax IR would be anytime we see something that's an impure function, we're going to analyze it to the fullest extent that we can, and let's see, never mind the halting problem, we're just going to try to inspect it. And we're going to do that every single time we find an impure function, which isn't really what we want to do overall. So the introduction of optional Boolean as the purity instead of Boolean would be specifically to allow us to delay the inference and to state when inference is already complete. And so if we say null opt, then it's, yeah, we don't have enough information. Well, so this is now, or this would be the default value for the is pure. This is handled both on the C++ and Python sides of the API. To make sure that we don't break backwards compatibility, because not all things are, we'll see, implicitly convertible. This PR also, if you call it with an explicit Boolean, still provides an explicit Boolean that you can use. And so if you are calling it with, I have made this to be a pure function, it is pure by construction, and we don't even need to do any analysis because it's already done, then those use cases still work, and it is backwards compatible with them. And so changing the default means that we don't need to hunt down every case where the default of purity needs to be replaced with a default of none, which is a much better way to handle it or especially for use cases outside of TVM. And so right now, it's just sort of a minimal example. Make sure that everything compiles, everything runs, because this is something that would impact the relax IR overall. But I think it's a beneficial change because it means that we have defaults that match what information we've been provided with, and we have a way that we can specify how those defaults should be updated.
Yes, yes, this is definitely, I think, a change for the better. I think this is making me regret making it a Boolean in the first place. That unknown we probably should have started with an unknown value. Um, my concern, so I think we might not be handling the worst case. The worst, if it's not, and we might need to add this to test cases. So if you look, I don't know if I actually wrote this one. If you look at the test cases for the mutual recursion detector or the recursion detector, you'll see there are all sorts of really nasty mutually recursive programs you could write. And I don't expect users to ever write this on purpose. No,
Mm-hmm.
no, it's true. The problem is that when you have
Is there
cases
a
like
function
this
I can
lurking,
pull up or is there a location where this is that I can pull
it's
up?
just in it's I think test analysis detect recursion, something like that. It doesn't matter.
Okay.
We don't need to actually look at them. I can describe plenty of them. I guess think of it this way. I could describe a few. They could be described very succinctly. So imagine you have a recursive infinite loop. Like literally, you just have define f and return a call to f.
Mm-hmm.
Whatever analysis we have for purity needs to be able to handle cases like this and their mutually recursive counterparts. These are kind of the worst cases where, like, imagine practically nothing goes on except calls to these functions with unknown purity.
Mm-hmm.
This is where it gets, like, again, this is the kind of case where we need to make sure we handle it. Not because I imagine users would actually write this code, but because I don't want people to get into situations where they write some code and the compiler crashes
Mm-hmm.
because we don't handle it. Um, so it's not hard to handle, mind you.
Yeah,
I think
I've been thinking of it as a graph flood fill problem where
yes, yes,
rather than having it be something that is recursively looking each time it inspects a function. And so something like any calls to, let's see, yeah, any calls to pure functions do not change the purity of the function being inspected. Any calls to unknown degrade the current function to a maximum of unknown. Any calls to impure degrade the current function to to impure and known to be impure. And then that this would and then anything that remains after that has been propagated through is pure. And so this is
yeah,
essentially saying the same as the C++, no infinite loops. Infinite loops are undefined behavior. Therefore, we can assume that those cases, everything terminates eventually.
yeah. I mean,
And
they don't
so,
even need
mhm.
they don't need to be infinite loops per se. Actually, well, no,
well,
okay. If they're not
well,
infinite loops, then yeah, the inference will be it'll be easy. Yeah, the inference will be like very easy. But
mhm.
yeah, the infinite loop case we do need to we might need special logic for that.
well, I think the infinite loop is just a point. Let's see, in a call graph is just a pointer to itself,
Yeah,
and so that is stating if the func the if x is pure, then x is pure.
yeah.
And
Um,
if x is impure, then x is impure. It doesn't actually give us any information.
yeah.
And so some way to break the tie would be to, and so this is why sort of the everything eventually terminates is a useful assumption to, or for the analysis, same way as it is for C++, because then we can say this thing must return eventually. Therefore, the call graph is sufficient.
Yeah. Um, I'm trying to think how I would describe this. Because actually, now that I think of it, this is not an analysis I've actually written. Yeah, so the single recursive function case is very easy. The one that's more annoying is when it's mutually recursive, when you have many of these and you have a cycle of these calls. that's where you need to, make sure you handle this sensibly, because that one is, again, a little bit
Hmm.
harder to detect. You need to actually construct the graph.
Yeah, and so I think we will need to construct the graph because
Yeah,
uh and so that would be within an IR module having a graph mapping each function to the functions that can make calls into it. And so we have to, because all the information flows from callee to caller. And so rat and so if we say everything defaults to pure, unless local analysis says that it is impure unknown, and now we iterate pushing information from the current function upwards to its callers. Each time you push it up, if that changes the purity of the
yeah,
caller, then it needs to be pushed up again. And
yeah,
so it's
yeah. It's a fixed
standards.
point.
Yeah, and we can get the fixed point because we are only ever allowed to decrease the purity of callers while inspecting a specific callee.
Yeah, yeah. The algorithm is not hard. The thing that the part that's a design concern is this needs to happen at some point. So
Correct.
in the PR
Mm,
discussion, one of them, you had the good idea that this should happen when we get rid of data flow blocks, because that is the point
mhm.
where we must know purity. Um,
Well, I would say not so much the point where we must know it, but the point where if we don't know it by that point, then we may have done invalid
yes.
optimizations and we would no longer be able to catch it.
Yes. Yeah, that's actually a good point too. That it might not be the best for debugging to catch these errors late. That it might
Mhm.
be good to catch it early. Um,
And so one thing that I think is very promising for the PR that had the inferred purity from local inspection only, this had many, many fewer CI failures. And so what that tells me is the vast majority of cases are handled with solely local function analysis, which we
oh
can
yeah.
do
Oh
inside
yeah.
the relaxed function constructor. And so everything after that is handling edge cases, but we already can handle the overwhelming majority of cases without running into them in the first place.
Yeah, so yes, absolutely. I don't expect this to be a common situation. So that might suggest that doing this late is probably fine because it's not going to be a common case. This is not something where people are going to be cursing the idiots who implemented the compiler when they get an error. I hope not. So okay, that sounds to me like a good reason to do it late. Because yeah, I mean, if this were code, if we were writing like an OCaml compiler, then no, we should not defer this. People are going to be writing code like that all the time.
Mm-hmm.
But yeah, so yes, you're right. This is not a common case. Local inference is going to be good enough 99% of the time. It's okay. I'm fine with that. Suits me. Okay, let's see. Any other design concerns? Because that was the biggest one for me. I think because otherwise things are pretty clear as far as, for example, subtyping goes. So actually, I was thinking about this. Which way should the hierarchy go? I guess is definitely impure a super type of unknown? I think yes, but I don't think it matters very much
Uh,
which one is the super type of the other.
so let's, yeah, I think it sort of depends on context, which is a worse answer than there being a clear one. Because if your question is, should I throw an error at this point, then unknown purity is, or I encounter something inside a data flow block. I am trying to decide whether I should raise an error for its being in that location, and I find that it is a unknown purity. I should not throw an error at that point. because, well, it could be a pure function. And so just that the analysis hasn't been performed to see if it is or not yet. And so from that perspective, the pure function is a subset of unknown. And
Yes.
see, on the other hand, there are points where I'd want to say this analysis is only, or this optimization is only valid if the call is a pure function. In that case, I want to check definitively, is this optimization allowed? And if I cannot prove that it's allowed, I will not run it. Let's see. And so in that case, let's see, the the unknown purity does not have the optimization applied. And so in that case, pure function is not acting as a subtype of impure function or of unknown, because I'm looking for a definitive thing. And so
Oh,
I
yeah,
I think
but that's okay actually. Oh, wait, hold on. Maybe I'm not following correctly.
or I should
Because
say, there's sort of two different questions that we can ask. We can ask, is this impure? Or we can ask, is this not pure? One of
yeah,
them, and those are different answers. Or sorry, is this pure or is this not impure? Where is this pure is the question that gets asked for, can I do an optimization that see, relies upon purity being present? Is this not impure? Is the question that gets asked if you're trying to verify whether something is legally allowed to be in a spot that forbids impure functions.
yeah.
So the
Yes,
way
that's
that
why I prefer to say this in terms of, definitely pure and definitely impure, and then unknown is possibly impure.
Mhm. Which, to be fair, is exactly what the optional bool gives us.
Yeah, exactly.
And so that way we can just go dot value or, and that gives us the let's see, location dependent defaults.
Yeah. Yeah, yeah, okay. For subtyping, I was just wondering, purely as a question, what is a member of which type? So I think it makes sense to make unknown a subtype of impure
Mm-hmm.
because of this. Um, but I think it kind of doesn't matter because technically those two sets they're the same size. If you consider pure to be a subtype of impure, those two sets are going to be the same size. They will, exactly the same members. Um, so it doesn't matter. I don't think it really matters as far as
Well,
how we implement our subtyping check.
except
Um,
that, see, if we consider pure to be a subtype of impure, then we're throwing a lot of errors right now that we shouldn't be,
oh yeah.
because anytime we do a well-formed check, we are throwing an error if we see purity equals false.
Oh,
If
wait,
that allows a pure function to be in that spot.
wait, hold on. Where is this being thrown? Because yeah, because I thought the way we already implemented it, like, yeah, we are considering pure to be a subtype of impure.
So this is inside, say, wellform.cc and sharing my screen. Now
This
all
is
the world will know that I am using Emacs and the Vim people will come to get me.
well,
Uh,
I'm an Emacs person, so you're fine here.
Here.
Okay. Impure. Oh no, this is fine. Yeah, yeah. Impure occurs within a function. No, that's fine. That's interesting. So how is find
Like,
impure
so
call?
if we are
Oh wait, I
saying that
implemented that. I should know how that's implemented.
I changed the implementation
Okay.
at one point as well, but see, so it's mea culpa as well.
Oh, I see what you're
But say
getting at.
if we are saying that
Okay.
pure is a subtype of impure, then this is not a problem. This is just, hey, yeah, it's inside a data flow block, so yeah, it must be pure because that's where we put it. The fact that it's labeled as impure just means that it's one of the pure functions that are a subset of impure functions.
Oh, this is really interesting now. Oh dear. So we
And
might,
so,
yeah, you're right. That's the way it's implemented now does not bite us, but if it had been implemented a different way, it could be biting us.
mhm.
That is very curious. Yeah, that's not a good specification then. Um, so this might be worth, okay, thank you for bringing this up. This is worth thinking about. Um, so maybe now that if we are adding unknown purity, maybe it would make sense to make impure kind of a different beast from from just the super type, like making it just a separate branch. Um, the reason I thought of impure as good to have as a super type of pure is that if you have a function whose signature takes an impure, if you're taking a function argument that's impure,
Mm.
if you pass a pure function to it, that's safe. Like nothing's gonna break by passing a pure function to something that expects
So I
something
think that
impure.
starts running into which types are covariant versus contravariant.
Yes.
Because if I return a function that, or because where it is on the function argument versus return, uh, drastically or changes which replacement is allowed. If I pass a pure
Yeah.
function into as a callback into a function that allows an impure argument, it isn't an issue.
Yes.
If I
The other way
re-
is an issue. Yeah.
if I return a uh let's see, pure function, actually this would be subtyping of pure subtype of impure in the both directions. Shoot, why am I?
Yeah, I don't think this one is not an issue actually
Yeah, you're
because
right.
returning something pure, yeah, because impure is always saying like I'm willing to tolerate effects, and pure is saying, well, I don't have any effects. So if you're willing to tolerate effects, that's great because I don't have any. Um, like,
Hmm.
so yeah, so I wouldn't want to. That's why, yeah, so that's why the subtyping was there in the first place. That's why I don't really want to get rid of it because I don't want I guess what would be the alternative? A user kind of would have to cast it to impure. Like, would they need a cast? Would they need
So
to
I
do
think
something?
it's not so much that we have, I would almost go, we have types of ways that, or we have contexts in which things are allowed and where they are not allowed. And
Yeah,
we have, yeah, I've been seeing it sort of as context for things being allowed and optimizations that have requirements. And so not so much which is a subset of the other, but seeing it as which of these require purity.
yeah.
An
Let me
optimization that
update the notes here.
requires. Mhm.
I'm just gonna get this down. Yeah, actually, Eric, no, that's good. I think for optimizations, it makes sense to think about what's allowed, what's not allowed. For things like checking function signatures, though, that is kind of straightforwardly, typing.
Mhm.
So that's why I phrase it that way.
Mm.
But this is really interesting. Okay. So yeah, okay. I'm just writing down what we've been talking about.
Yeah, because it's almost like impure functions and impure expressions follow different rules. An impure function is or a pure function is a subtype of impure function. Anywhere that an impure function can be used, you can use a pure function. A pure expression, uh no, still thought, yeah, I think I'm still coming down to impure. Okay, actually no. Any anywhere that a impure function, anywhere that an impure function is accepted. If somewhere requires a pure function, This is then in a location where a pure function is required. We can provide either pure or unknown at compile time, but we must realize it at some later point.
Yeah.
And so, same way as the shapes have to match when you're doing your map mul, does not matter if they are, let's see, there or not, or at compile time, they're gonna have to match by runtime eventually. And so it's not so much that, and so I think I would still say that pure functions are a subset of impure. However, uh, unknown, yeah, it's almost like we can label the same function as either pure or impure. The labeled function is not the same as the original function that we applied the label to. If I have two different functions that are absolutely identical, except that one of them is behind a door saying impure, and the other is behind a door saying pure, the one that is labeled as impure may not appear in a data flow block.
Yeah.
And
Yeah.
so I think that's where I would say that it's still that pure functions are a subset of impure. However, the labeling of it changes it to a different function.
Yeah, I agree. Yeah, I mean, exactly. If the user went out of their way to label something explicitly, the compiler should respect it. Plenty of languages do this. In C++, you can label things. Like if you label something no except, the compiler is going to treat it differently, regardless of whether it actually throws an exception or not. Or not, the compiler will respect
Oh
the
yeah,
label.
it's the label is important because you've told it you don't need to look behind the curtain.
Yeah.
And we kind of have that with the force pure attributes on the
Yes.
functions.
Yes.
And I'm almost wondering if this supersedes it.
Do we
If we
still?
have,
That's a good question. Do we still need it? Yeah.
because if we have optional purity, then optional purity and pure, yeah, the fact that we then have an explicitly, yes, this is pure. Oh no, because let's see, the only difference would be, that if the function body is mutated, force pure attribute means you, after mutations, you still don't need to look into it.
Exactly. Yeah,
But
that's the whole reason it's
mhm,
there. That's the whole case it's meant to handle. Yep.
mhm. Yeah, whereas the pure attribute could be, hey, this, if something else in the environment comes out, you might want to take a look at it again for unknown purity. But also any other mutation could make it be impure, so you're going to have to keep looking at it. I like
Yeah.
that.
Yeah.
Yeah, one is
Yeah, we could think
preserved through
about
mutation.
so Eric, I think your TIR purity check, I think you actually do handle the case of allocating a value and mutating only the value
Mhm.
you allocate. I wonder, is that feasible for us to do and relax? I think the possibility of opaque external calls probably says no. We don't know if an external call allocated something new, or if it's just aliasing an existing value. Um, but maybe that's another situation where 99% of the time we can correctly infer. We would still need the escape hatch for the, 1% that we can't infer it. But that's worth also thinking about. Um,
Yeah, and the mutation occurs more often on the TIR side because it doesn't have the same set of built-in operators, and so it's there to be mutatable for
yeah,
any buffer. Whereas the in-place operate or the in-place overwrites in relax are not the default.
Yeah.
But yeah, it's all. And so that would all. If we handle it in TIR, but we don't handle it in relax, then that would almost be a, hey, this thing can suddenly become known to be pure when it gets lowered into something where the analysis can be done at a granularity supporting that check. Which I kind of like that overall of we do the best analysis we can in both cases, but I'd like that best analysis to be as good as can be in both cases.
Yeah. Well, I think that was Tianqi's kind of design principle from the start to use best effort analysis,
Mm-hmm.
whenever possible. And yes, we should work to make sure our best effort is in fact our best
Yeah,
effort.
and that's where uh yeah, best effort sometimes becomes therefore it cannot be relied upon to be any specific level of effort.
Well,
For me, I tend to
that's a
take best
trade-off.
effort as anytime I run into an issue, it is acceptable to improve the best efforts.
I mean, yeah, we should certainly constantly be improving it. It's funny. I don't want to go on a tangent, but that kind of was Rust's approach, right? Where the early versions of Rust, didn't go too crazy on the linear typing, but as time went on, they improved the inference more and more, so that people don't have to go crazy with the borrow checker.
Yeah, and
Um,
I really like that as just sort of the start with a safe set and expand it outwards rather than starting with a unsafe set and trying to carve off, well, I got hurt doing this specific step, so I'll make a check for that specific
yeah.
thing.
Good to think about.
Mm-hmm.
Okay, then. So I think we've covered most of the design. So this change, as your PRs show, there isn't that much that would have to change. Thankfully.
Mm-hmm.
Um, I do want other people to, comment on this before we hit the button and say, let's do it.
Yeah, I think
But I
I'll
like the
post
idea.
it
I think it definitely
in our
cleans up
internal channel
some.
as well.
I'm sorry, Eric, I cut you
Oh,
off.
sorry. I think I'll post a link to it in the internal channel as well, just to try
Yeah,
to
we can
get.
post it internally, post it on a Discord as well.
Mhm.
Just get it out. Yeah, I guess maybe the forum post and the Discord post for the meeting. Maybe people just are so used to seeing them that they have their eyes glazed over. Maybe if we
Mhm.
make a specific topic, they'll respond. That's probably a good step. Um, okay, let's think. Is there anything else we want to cover before we sign off?
So something more exploratory. This was something that came up in entirely different PR. Can't remember exactly where, but the let's see. Currently, there's a number of different operators that will assert my argument must be a tensor. They throw in error if the argument is an object, but this feels like it shouldn't be happening until the legalization step because, well, that our object struct info could be a tensor. And so I'm almost wondering in those cases, and like the same thing is true for some of the shape checks. These two dimensions must be equal. Well, we can't prove that they are equal right now, therefore we're throwing an exception. Or this one has an unknown shape.
Mm,
And so what I was thinking about a little bit this morning was this feels like something that should be part of normalization on an operator to operator basis, not part of shape inference. And the normalization that it would do would be to insert match casts in order to resolve unknowns.
ooh, that's
And
interesting.
so if you have uh or because a match cast is already a conversion between types that is a fallible conversion is allowed in all of the is treated as pure for the purpose of relax purity tracking, and is allowed to introduce new definitions, is allowed to introduce correlations between symbolic variables, is allowed to impose restrictions upon the incoming types. And so we have a number of cases where we have operators that impose additional preconditions. And we have a tool that can be used to state a precondition. And so what I'm almost thinking is something like, if you have a say matmul of object by object, this is not an error. Well, I should say currently it is an error. We could instead state this is a thing that, or it will be normalized to match cast of its arguments in from object to tensor on both sides and then call it. And so this would occur anytime it isn't already a tensor. So we have an idempotent change, and now we have tensor arguments. And one of the things I was thinking, because then this goes to something that I was thinking would be a useful pass of match casts should always be moved as early as possible.
Mm.
Stating it that way as anytime you have a precondition, we want to hoist that precondition as early as possible. If you have a function that accepts an r.object and then does a match cast to it as an r.tensor, we should rewrite that to be a function that accepts an r.tensor. Because it already is only accepting an r.tensor, it's just that we've hidden that inside the function body.
Yes. Mm. I mean, well, and yeah, and if you read the spec on how function struct info checking works, all right, like literally desugars into the same thing as a match cast. I don't know if that's how we actually implemented it, but it's supposed to.
Yeah, the what I think, and I kind of want to at some point desugar the match cast in the opposite direction and have something like an unchecked conversion, because with the different like shape and stride checks, that allows them to be expressed within the relaxed language itself rather than externally.
This is a very interesting idea.
But I would say there's one additional thing you can do with or with it being part of the signature that you can't do with it being part of the body. And that's that you can then hoist it up even further into the global variable that represents that function.
Yeah.
And now it becomes something that can be inferred that can be used to provide better checking at the caller sites as well.
Mm.
And
Yes.
so same goal of just hoist the preconditions, but there's nothing that says that that hoisting needs to be within a single function.
Mm. That's true. That is very, very curious. Only worth, yeah, worth digesting.
And sort of and now we get to why would we want to do that? Because then that gives us a better default in cases where we don't know something. And so same way that right now, all of the not Rust, all of the relax, say struct inference is only flowed forward. Hoisting match casts to earlier locations would provide us a way to flow it backwards and check it early as possible.
Yeah, better type
And
checking.
so, and what that would mean is all of a sudden, it doesn't matter if we have unified our symbolic variables to say, hey, this is the one and only one hidden size. It's, well, you did a matmul of two things. that produces a constraint on the dimensions of them that they must be the same, or that one of them must be one, because we still have the broadcasting rules. But that could then be expressed as a match cast, which then imposes a restriction on the symbolic variable, which then can be hoisted earlier, and bam, now this is a function that has one fewer symbolic variable,
Oh,
which means that we don't need to care if we wrote it the easy, convenient way with every single thing as its own dynamic parameter, because those constraints are present from the operations,
yes.
not from
Oh, this
us
is
hard
this is
coding it.
good. Yes, that is good simplification. Very user friendly.
I like
So
the
that,
idea. Okay.
thank you.
Yeah, I like this. This is a great idea. Um, I'd like to, yeah, I'd like to think
Oh yeah,
about
I need to
how the
chew over the
implementation.
idea, the implications of it, but
No, the implementation I think is what to think about, but that wouldn't be, yeah, not too hard to do, I think. Um, yeah, starting. So yeah, if you have a bunch of match casts, if you can move them up, yeah, the question is, I guess, yeah, deciding when things can be moved into the function signature. Um, so match
so
casts, I presume, on parameters, I guess
a
is the
match cast
condition.
on a parameter.
Yeah,
But you
that's
can
what you.
also do something like, if you have a match cast on the shape of an element-wise operator, and the match cast is on the output of it, you could hoist that up to be the match cast on an input of an element-wise operator.
Yes. Okay, so we might need per operator rules then.
Mm-hmm.
Okay, that's yeah, this okay, yeah, we should try to work out this design then. This is a very interesting idea.
Yeah,
Okay.
and so I think I would almost just see it as, yeah. Oh yeah, I per operator rules, everything gets hoisted as early as possible in order to flow them opposite the direction of normal struct inference.
Mm-hmm. Yeah.
Ah, I think that was sort of all I had on that topic, though that
That's a yeah, it's a curious one. Okay, yeah, that's another one we should try to get wider comments on. So yeah, it sounds like that one would require quite a bit of quite a bit of engineering because we would have to change many operators struct info inference rules into normalization rules that add match casts. Although I agree with you 100%. Now that you pointed out, you are right that that match cast is a very powerful tool for asserting conditions. That it tells the type system assume this, but also will check it dynamically.
mhm.
Very powerful tool. Um,
Yeah, because it's
I
sort of
guess it does create
mhm.
the trade-off that it does mean more work dynamically. Um,
So
but
I would say it is more work dynamically only in cases where we can't hoist it up. If we
that's true.
can hoist it up to the function signature, well, then it becomes equivalent to having written it with one fewer dynamic variable in the first place.
Yeah, yeah.
And we're
Uh,
already checking those.
yeah, okay. Yeah, so I guess the problem is we don't have right now infrastructure. So this would be just another thing we have to do. Right now we don't have any kind of pass or infrastructure that like for combining constraints, right? Like let's say you have match casts on the same underlying value. Right now we don't have anything to say that, well, maybe we could express this as one cast. Um,
Mm-hmm.
and
Yeah, the
that would be
closest we have
also
is, yeah, because we have the struct info LCA, but we don't really have a struct. I feel like I wrote a struct info intersection somewhere, but I can't remember where it would be.
the spec should have it too, but on paper only,
Oh
not
yeah.
in. Uh, yeah. So okay, this is definitely a good thing to stew on. Maybe yeah, we should definitely present this to a bigger group or when we have more
Mm-hmm.
attendance. Um, I like the idea. So we are about at time. Um, so thank you for the discussion, Eric. For those listening to the recording, please remember that in 2 weeks we will have a vertical focused meeting. So bring your topics. With that, we can conclude. I'll see you all next week, most likely.
See you
See you.
later.
See you.